So this is a presentation I gave to a major Belgian bank who wanted to learn about quantum algorithms and whether or not it could help them with their financial computations. And since my research topic is post-quantum cryptography, I know a tiny little bit about quantum algorithms, and I thought I might as well give you guys the same presentation. So that's what this is about. This is a two-part lecture. In the first part, I will cover the first 3 points, and in the second part, which will take place on Wednesday, I will cover the second 3 points. So I added a couple of slides that are relevant to people with respect to crypto. So right after Shor's algorithm, there are a couple of very specific crypto slides. If you're not interested in that, please forgive me. Otherwise, all the better. All right. So first of all, I'm not a quantum physicist. I don't build quantum computers. I don't know how far we are from their construction. If you want to know this, you should consult a physicist. I'm a theoretician. I deal with quantum algorithms. I don't deal with the matter, the physical matter. So, applications of quantum computers. Quantum computers were first conceived as a method with which to simulate quantum mechanics, meaning many body systems that interact quantumly with each other, so as to predict the behavior of larger molecules, which can be really, really interesting for science, but also for industry. For instance, the behavior of proteins can lead to very interesting applications for the development of drugs, or for nanomaterials, which don't even have to rely on proteins, but can also be constructed from other materials whose behavior can only be understood in an appropriate quantum model. So there is definitely a lot of industrial demand for these computations. And it's also possible that a quantum computer can help predict the behavior of really, really small circuits. Because today already we're starting to hit the barrier where circuits are getting so small that circuits designers have to take into account quantum effects. And this actually has a bootstrapping potential, because maybe the simulation of really small circuits can lead to a better understanding of really small circuits that can perform these computations. So there might be some potential for bootstrapping. Another application of quantum algorithms is to break crypto. And if you're going to design crypto that's supposed to resist attacks by quantum computers, and you want to prove the security of this crypto, well, then you have to take into account quantum algorithms that perform this attack. So that's why some people need quantum computing. And it's also possible to do crypto with quantum computers. This is a different form of cryptography. Usually we work with mathematically hard problems, and we use these hard problems to protect information. In this last case, problems aren't really mathematically hard. We're instead relying on the physical property. We're using physics to protect information rather than mathematics to protect information. But there are some interesting applications here also. And sometimes even you don't need a full-scale quantum computer capable of arbitrary computations. Sometimes very simple manipulations on light photon polarizations, for instance, can do the trick. Quantum computers are often hailed as generic speedup, and that's sort of half true. It is definitely true that you can speed up any brute force search, and if you're going to find an optimal solution to a problem using brute force search, well then I guess you can also use Grover's algorithm. Use quantum algorithms to engineer the speed up. But the speed up is only rather small. So in the second part, where we see Grover's algorithm, we'll see that the speed up is only in the square root of the search space. So this is not the ideal application of quantum algorithms, because there will be many tasks that are currently infeasible and will still be infeasible on quantum computers. And one thing we project with a large degree of certainty is that quantum computers will not be friendly with big data, because quantum computers tend to rely on very cold temperatures, and it takes a while to get all the data into the quantum computer and back out. So whenever you hear people selling the new information age as quantum computers and big data, that's where your red flags should go up into the air. And when they sell quantum computing with finance, well, that's the original reason for my invitation, and I did think about it, and I think there are a couple of applications that make sense for quantum computers in finance. I'll get to that in the next lecture. So it may be a bit of a hype, but blockchain is everywhere, and let me stress that there is really zero intersection with quantum algorithms and the blockchain. Furthermore, beyond zero intersection, if you want to do money anyway, and you have access to quantum computers, you don't need a blockchain. Because the no cloning theorem of quantum information states that you cannot clone quantum information. You can use this for money, in which case you have uncounterfeitable money. Or you can use it for identities, in which case you have uncounterfeitable identities. So that's an interesting application. So the problem that I mentioned here with generic optimization, that's really the case with NP-complete problems. We really do not expect quantum computers to have a meaningful speed up here. It will be square root speed up, but not more. But then, of course, maybe the square root speed up is enough. So in general, when you're looking for applications of quantum algorithms, you want to find something that does not take a lot of data to describe, but still has a large complexity, and preferably has a lot of structure also. So just finding a pre-image to a hash, for instance, that's small data and big complexity, but very little structure. So that will still be very difficult. On the other hand, finding the prime factorization of a large integer, that's small data, big complexity, but also has a lot of structure. And that's where quantum algorithms excel. I do post-quantum cryptography, so I break crypto and prove its security, or at least I try to. So if you have any questions about that, I can go in as much detail as you like, I hope. So, if you want to learn more about quantum algorithms, more than I can teach, or if I'm not available for questions, please consult the Bible, which is obviously the Nielsen and Chuang book, which is cited by any meaningful paper on quantum computations. This is a fantastic book. I recommend reading it. And if you don't think this is profound enough, I can also recommend some poetry, which is obviously Scott Aronson's Quantum Computing Since Democritus. I'm being serious here. This is lecture notes disguised as poetry. It's a series of essays, I guess, following course taught in 2005, I think, about quantum computation. It's a very intuitive introduction. It's a very layman introduction. In fact, he goes out of his way to avoid formulas at all cost. So if you're into abstract science fiction-like ideas, you will love this book. Then there's the zoo, in case you didn't like the first two enough. And I mean by that, obviously, the quantum algorithm zoo. NIST is maintaining a list of known quantum algorithms or known problems that quantum algorithms can solve. And then there are a couple of lecture notes in circulation. I recommend the lecture notes by Preskel, but those by de Wolf are also really, really good. And they also cross-cite other lecture notes, which I did not look, but are probably also really, really good. So that was the introduction. So let's get to the meat of the matter. Quantum computation, postulates. The first postulate, well, maybe I should start with the obvious fact that on a classical computer, a bit is 0 or 1 and is represented by a voltage on a wire. Whereas on a quantum computer, we deal with qubits, and this is represented in the state of quantum particles. For instance, the spin of an electron or the polarization of a photon. So the question is, at first, the question is, how do we represent the state of a quantum system? And quantum physics gives us this answer. A state is fully described by a vector of 2 to the k complex numbers, where k is the number of qubits. So if you're going to have k electrons, and each one of them has an up or down spin, then you have 2 to the k complex numbers describing in full the state of the system. And this complex vector has length 1, and that's a state. Every quantum state has length 1. So this odd notation is called ket notation. It's sometimes handy. It really just indicates this is a very large vector. When we flip the angle bracket and the straight bracket, then we take the complex conjugate transpose. So this is a neat way to write the inner product, and this is basically saying that the length is 1. So we have a state. What does a transformation of this state look like? Well, every transformation associated with a valid computation is unitary, which means that you take this vector of length 2 to the k, and you get to apply a unitary transform to this vector. So unitary basically means it retains length 1, sends vectors of length 1 to vectors of length 1 always. Also means that if you take its conjugate transpose and multiply it by its original, then you get the identity. All right. So we have states and transitions. What happens if we adjoin 2 different systems? How do we describe the resulting system? So we start from 2 states, describing 2 different systems. How do we describe the combined state? Well, we just take the tensor product. What is the tensor product? No problem. I have a slide for that. So let's start with the inner product. We have two vectors, and we take two bilinear products and we sum them. That's standard inner product. Shouldn't be surprising to anyone. But there's also the outer product, in which case we take all bilinear products and arrange them in a matrix. Right? So the third element on this list is the tensor product, also known as the Kronecker product, where we take all the same bilinear terms, but instead of arranging them into a matrix, we arrange them into a vector. So that's, you can think of this as a fancy way of saying the tensor, saying the outer product. It's just vectors instead of matrices. All right. So the composition is given by the tensor product, which, by the way, guarantees that if you start from two systems whose state is length 1, the composition of those two systems also has length 1 of its state. So then the last question is, what does measurement do? So measurement can be described as a series of operators, which is a function of an orthonormal basis for the state space, and it collapses the state to one of these vectors with a given probability, which you can find by taking the inner product with this basis vector vi and the state, and that. So this defines an amplitude, and you take the square of the magnitude of this amplitude, and that gives you the probability of measuring bi. And if you measure bi, then the state will have collapsed to bi, meaning that all other possible worlds are no longer in existence. So you can think of these bi up until bk as vectors associated with every possible bit stream. So let's have an example. We're going to use a 1-qubit system, which obviously has two basis vectors, 0 and 1. And in order to describe this system in full, we require two complex numbers, alpha and beta, such that their length is 1. And then when we measure this system psi, we find 0 with probability magnitude of alpha squared, and 1 with probability magnitude of beta squared. So the amplitude is really just the square root of the probability, or phrased differently, the probability is really just the square of the amplitude. The difference is that the amplitude gets to be complex and negative, whereas the probability has to be positive between 0 and 1, and so on. All right. More example. So what if instead we have two qubits, both of which are set to 0? Right? So now the question is, what is an appropriate basis for this system? And we find an appropriate basis by starting from the basis for each individual qubit and taking their tensor product, taking the pairwise tensor product. So this gives us 4 basis vectors associated with each possible bit string. And with each basis vector there is an amplitude, which is a complex number. And the vector of these complex numbers must sum to 1. In this case, it trivially sums to 1 because alpha is 1 and beta, gamma, and delta are 0. This means that these terms really cancel, and we know for certain that the system is in the state 0, 0. That's all right. But what if we apply a unitary transformation of this form? right? Well, we can compute what that will give us. So alpha is 1 and beta, gamma, and delta are all 0. So basically, we really need to look at this row, this column, excuse me. This is the new value for alpha, and this is the new value for delta, whereas beta and gamma are still 0. I shouldn't be explaining matrix vector multiplication, but this is the state that you get as a result. So this represents the superposition of 0, 0 and 1, 1. So if we were to measure this state, the probability of measuring 0, 0 you can find by taking this amplitude and squaring it, and that's 1/2. And the probability of finding 1, 1 you can find by taking this amplitude and squaring it, that will give you 1/2 as well. And this is not really new, right? We already know this. And I actually brought something to illustrate this. I have here 2 envelopes, both of which contain a coin. And I'm putting both envelopes face up, and I can tell you with 100% certainty both envelopes contain either heads up or heads down, but always the same. Meaning that if you look at one envelope, then you instantly know the value of the other envelope, regardless of how far they are apart. But I'm not telling you whether this value is heads up or heads down. You have to look to find out. So this is really just reflecting a very similar principle to what we already have in the classical world. So let's look into the difference, not the similarity. The first mode of computation that we already know. So in this depiction of computation, time runs downwards, and every node represents a possible state of the computational system, and every edge represents a possible transition. And in the deterministic mode of computation, there is ever only one possible transition. So after 2 time steps, I will choose at random one of the available nodes to color, and the question is, what is the probability of observing that node after 2 time steps? Well, in the deterministic case, it's really, really easy because there is only one node at the bottom. And that's because there is no possibility for branching because it is deterministic. Stuff gets a little more interesting when we get probabilistic. So in this case, in the first step, the state takes a right branch with probability 0.2 and takes a left branch with probability 0.8. Notice how the probabilities must always sum to 1. So then I color a random node on the bottommost layer, and the question is, what is the probability of observing this state after 2 steps of computation? Well, we find this probability by summing the contribution from this path and the contribution from that path. This is one way to depict computation. All right. What does quantum computation look like? Very similar, except the big difference is right here. You can have negative amplitudes. So once again, it's a graph with the possibility of splitting. And at every step, the squares of the amplitudes must sum to 1. And the only difference is negative signs. So then the question is, once again, I colored a random node. The question is, what's the probability of observing this state when we measure after 2 steps? Well, we determine this probability by summing the amplitude associated with this path and the amplitude associated with this path, and then squaring, and that gives us the probability. But because there is a negative sign here, these amplitudes actually cancel to some degree. And that's the key difference that we don't have in the probabilistic case. You can have cancellation of amplitudes. Alright, so I left out one possible mode of computation. I was wondering if any one of you could tell me what it was that I left out. Here's a hint. As far as we know, it's not physically realizable. But it's still mathematically useful. I'm speaking, obviously, of non-deterministic computation. At every time step, the state takes all possible transitions. So, in reality, the state splits. And, well, the probability of seeing this one node at the end is 1, because the probability of seeing any one node is 1, because probability is meaningless in this world. So this is useful because it captures the computational model associated with problems that have a solution that is efficiently verifiable. Because you can cast this solution into a description of the path to follow that will cause your non-deterministic program to accept, to verify. So I included this picture to illustrate that there is still a very large gap between quantum computation and non-deterministic computation. So the space of efficiently solvable problems in this mode of computation, that's NP complete. And the space of efficiently solvable problems in this mode of computation is presumably much smaller. Alright. So I've tried to convince you up until now that quantum computation really isn't that much different from classical computation. And now I'm going to offer yet another algorithm, yet another argument rather, to show that this is really true. I am going to show how we are already using probabilistic computation by using the postulates of quantum computation and modifying them to describe classical computation. So, a probabilistic system is fully defined by its probability distribution. Right? It associates a certain probability with every possible bit string. And, well, in the quantum case, we wanted the Euclidean length. In the classical case, we want all probabilities to sum to 0. So, one way to say that is that the L1 norm is 1. So what does postulate 2 look like? A valid computation is not unitary because it doesn't preserve the L2 length, but it is stochastic because it preserves the L1 length. Stochastic means that all rows and columns sum to 1 and that all elements are between 0 and 1. But what's interesting is that the state still takes 2 to the k numbers to fully describe, and state transition matrices still take really large matrices to describe. Alright, what happens if we compose 2 probabilistic systems? Do we still take the tensor product? Yes. Yes, we do. I have 2 coins here, each with the probability of either being up or down, heads up, heads down, heads up, heads down, which means that there are 4 possibilities in total. And 4 events come with 4 probabilities. So the tensor product is not new. And then how do we translate quantum measurement? Well, that's really just sampling. So we sample with respect to an orthonormal basis. Each of these bases represents a possible bit stream. And after we make the sampling, well, the probability of that one sample is fixed, has become trivial, because we know its value. There is no distribution of probability anymore, except 1 in that particular value and 0 everywhere else. So probabilistic computation and quantum computation is really very similar, and that enables you to quickly grasp the essence of quantum computation with only 2 very small steps. Step 0 is you have to start with probabilistic computation. You cannot just start with deterministic computation. Step 1 is you have to compute with probabilities instead of samples. Probability distributions. So at every point in time, the state of your system is described by a probability distribution. And only when you measure the value do you know the value and can you forget about the probability distribution. Right? For a meaningful quantum algorithm, you have to postpone measurement all the way until the end. And then in step 2, what you need is a state transition that is continuous as opposed to discrete. What I mean by it is that you can always take the square root or any root out of any computation. And this is what instantly gives you complex numbers and the L2 norm. Of course, taking the root of a computation might be difficult to implement in a circuit, and computing with probability distributions might also be difficult to implement in a circuit, but that's rather a minor detail. So I would pay no attention to the fact that quantum algorithms are usually described with respect to circuits and not with respect to traditional algorithms that describe how a state changes with if and else, if, else, for, and so on. So the way you create a quantum algorithm, or the way it works, is by using gates in your circuit that affect only a few qubits at a time. And those qubits that are not affected, their transition can be modeled as the identity transition, and for every gate we have a given matrix that defines how it affects its qubits. And by tensoring the identity matrices of the qubits that are not affected with the given matrix of the qubits that are affected, we can find the entire matrix description of the entire transformation. So let me say a little bit more about this phenomenon of interference, right? So we have a waveform generator which hits a wall, which has 2 perforations, and each of these holes in the wall becomes, become their own generators of waveforms. And these waveforms spread out, and at some point they start enhancing each other or canceling each other. And this phenomenon is exactly interference. If you would look at the amplitude of the wave at this point, you have a very large amplitude where the waves interfere constructively, and a very low amplitude where the waves interfere destructively. And this is exactly the principle that quantum computers exploit. So for example, here we have a very simple unitary transformation on a single qubit whose effect is the square root of naught. You guys are all familiar with the NOT gate. It flips your qubit, and this performs half a flip. Right? So let's see what it does. When we apply it once to a qubit that is initialized to the 0 qubit, then we get a uniform superposition of 0 and 1. And when we apply it a second time, then it's just the square of the square root of naught, which is just naught. What does this have to do with interference? Well, if you draw the state transition diagram, and I drew it a little verbosely, because this state is obviously the same as this state, and this state is the same as that state. We'll forget about that for a second. If you draw the state transition diagram, we start with 0, then we apply the square root of naught gate once, we get the uniform superposition of 0 and 1, and then we apply it again, and each of these states become the uniform superposition of 0 and 1, except in order to make this matrix unitary, we had to add this negative sign right here, meaning that the state 1 will be mapped to -0. So then the question is, what is the probability of measuring 0? Well, we take the amplitude of all possible paths to 0, the sum of the amplitudes associated with these paths, and then square it. But since these paths cancel exactly, the probability of measuring 0 is 0. And the probability of measuring 1 is 1, which allows us to cancel all the other terms and write just 1 up there. So this principle is destructive interference, simultaneously constructive interference, and this is the source of all quantum weirdness. So if you want to design quantum algorithms, what you need to do is to engineer interference. So the density operator is an equivalent description of quantum computation. Instead of describing a quantum state as a vector of 2 to the k complex numbers, the density operator chooses to describe it as a matrix of 2 to the k complex numbers. This is algebraically very useful, but for cultivating intuition, maybe not. This is very useful if you want to describe probability distributions over quantum states. For instance, when you have a quantum state generator that with probability 1/2 outputs the uniform superposition of 1, 1 and 0, 1, and with probability 1/2 outputs the uniform superposition of 0, 0 and 0, 1. Well, in that case, you would use a density operator, but you could, in principle, do it with the regular vector state described earlier. It's also really useful for describing partial systems. So your system, the complete system is larger than what you're interested in, and you want to forget about the qubits that don't affect what you're interested in. That's where you would use the density operator. And ultimately, it's not necessary. Most quantum algorithms can be explained and understood without reference to the density operator. One important note, though, is that when you ignore certain qubits, this is associated with an operation on the density operator, which is a matrix, involving a partial trace, and this operation is actually indistinguishable from performing measurement. Right? So you can treat qubits that have been traced out of your system because you're ignoring them as though they have been measured. But of course you're not allowed to know the value of this measurement. And once you reintegrate them back into the system, they retain the superposition. That's because that's the reason why you're not allowed to know the value of this measurement. So this gives rise to a whole debate. If tracing out is the same as measurement, does measurement really exist? And the many worlds theorists say, no, it doesn't. The Copenhagen interpretation says, yes, of course, measurement does exist. All right. So we've seen that quantum computation uses interference, but does the addition of interference really lead to different measurable outcomes? Well, in order to answer that question, let me go back to Einstein, who attempted to define existence, which is a difficult philosophical problem, but I think Einstein did quite well. He said, something exists if it has a state, by which I mean more than just a value, but also a way of describing how this state responds to changes in its environment. Something exists if it has a state that has a value that can be exposed through measurement. This value can be measured somehow. But this value must be independent of this measurement. Right? Because if it is dependent on this measurement, then how do we know it's not a property of this measurement? If it's dependent on this measurement, then it doesn't exist independently. So if these 4 bullet points accurately describe what exists and what does not exist, well then quantum mechanics describes something that does not exist. Because necessarily, in quantum mechanics, measurement influences the state. So this independence is not true. Or that's the prediction of quantum mechanics, at least. Einstein interpreted this to mean that quantum mechanics has to be wrong, which is by no means obvious. And so he wrote a paper, together with co-authors Podolsky and Rosen, attempting to show that quantum mechanics has to be incompatible with general relativity. So the idea is, we have 2 electrons, and we prepare them in this very special state of up-up or down-down, sort of like my 2 coins. And we send one electron to Alice and one to Bob on opposite sides of the universe, because there has to be a large distance between them. All right. And then quantum mechanics predicts the following possible sequence of events. If Alice measures up, then she knows instantly that Bob will measure up as well. And if Alice measures down, then she knows instantly that Bob will measure down. Instantly is the key word, because until the instant that Alice performs this measurement, Bob's probability of measuring up or down is 1/2. So somehow, Alice's measurement affects Bob's chances faster than the speed of light, because there's an instant transmission of influence on Born probabilities. Well, this is clearly incompatible with general relativity, because general relativity outlaws causation faster than the speed of light. Well, that's a rather good argument, but it does contain several very subtle assumptions. For starters, the assumption of realism, which states that objects' observable behavior is determined in full by its state. Well, you can always define the state to meet this criterion, but the difficulty is in simultaneously meeting the second criterion of locality, which states that an object's state is affected only by its immediate environment, which I guess means in space and in time. There can be no transmission of causation that doesn't travel through space and that doesn't travel through time. All right. So putting these two things together is what gives us local realism, also sometimes called local hidden variables theory. And Bell said we can test this theory. More specifically, he said it is possible to generate an experiment or a sequence of measurement apparatuses that produce measurement outcomes or variables such that there is a function of these measurement variables, which are probabilistic, and this function satisfies an inequality whenever you instantiate these variables with a classical probability distribution, but not if these variables measure quantum phenomena. So we can use this experimental setup to test if local realism is true or false, because if the Bell inequality holds in this experimental setup, then obviously local realism has to be true and quantum mechanics has to be false. Conversely, if some experiments violate the Bell inequality, then local realism is false and quantum mechanics might be true. All right, so how do we compute this? So let's start with a Bell pair. This is down, down, or up, up. And I'm going to use -1 instead of the traditional 0 because we're going to compute with these measurement outcomes. And then Alice flips a coin, and depending on her coin flip, she measures with measurement apparatus Q or with measurement apparatus R. And Bob does the same with apparatuses S or T. And then the result of this measurement will always be -1 or 1, and then they're going to compute a particular function of these measurement variables. So, if it is true that the system satisfies a classical probability distribution, then we have this inequality. The expectance value of, the sum of all expectance values of products with one added negation sign has to be less than 2. It's possible to prove this, but intuitively, the way you would maximize this quantity is by setting Q, S, and R to 1, in which case the first 3 terms are 1, but in that case, the last term will be 1 as well, and then you get 3 minus 1 is still less or equal to 2. And if you're going to shrink any one of these variables, then you will also, in order to shrink this, then you will also shrink the first few terms. So that's the So we can run a quantum experiment and then compute the value of this function, or rather, we can run it many times because it's an expectance value, and then test whether or not it satisfies less than or equal to 2. This is the Bell inequality. Bell discovered it, and then authors by the initial CHSH discovered it, and now people call it the CHSH inequality, but I don't think that does nearly as much credit to Bell as it should. Right. This experiment has been performed many times over, and experimentally the Bell inequality is violated, which indicates at the very least that local realism is false, and it might also indicate that quantum mechanics is true. Right, so armed with our newfound knowledge of quantum computation, can we predict what quantum mechanics is going to give us in this experiment? Well, first I have to describe exactly what these measurement apparatuses do. And you can plot them. So, since these two basis vectors are orthogonal, we can put them onto orthogonal axes, but in practice this would be the up spin and the down spin, or the other way around, in which case you need to double all the angles. So we start in the Bell state, the uniform superposition of up, up and down, down. And we have a computation L applying to 1 qubit, which really rotates by 22.5 degrees. So that would be going from Q to S or from S to R, one of those transitions. All right? And then measurement apparatus Q is defined as just measure Alice's qubit. S is defined as rotate once and then measure Bob's qubit. R is rotate twice and then measure Alice's qubit. T is rotate 3 times and then measure Bob's qubit. Right, so these axes really indicate how much is being rotated, and then it's worth remembering that there's interleaving, so R and Q and R belong to Alice, S and T belong to Bob. Alright, so we can compute the expectance value of Q times S, which is the probability of measuring the same qubit minus the probability of measuring different qubits. And when you work it out, you see, you take the state, apply the computation, and then compute the probability of measuring 1, 1, which you do by taking this amplitude and squaring it. But minus 1 will also give you a satisfactory outcome. So once again, you start from the state, apply the computation, take the amplitude of measuring minus 1, square this amplitude, and this gives you the probability, or rather, the expectance value of QS. On the other hand, when Alice's qubit is different from Bob's qubit, this happens when you measure up, down, or down, up. And in order to compute that probability, you start from the state, apply the computation, and compute the amplitude and square it. You do that twice because there are 2 events that you have to count. If you plot these measurements graphically, what you get is in the axis, in the basis, we're looking for the sine of this angle and the cosine of that angle, which you then need to square. All right. But the only factor that really determines how big this quantity is the size of that angle, because you can always apply a basis transformation to align one of the angles with the x-axis. So we already know the expectance of QS is this value, but that's also the expectance of RS and of TR. So then there's one quantity left in our inequality, and that's the expectance of QT. So how do we compute that? Exactly the same way. That's the probability of measuring the same thing minus the probability of measuring different things. And with some graphical intuition, you can easily see that this angle is the complement of this angle, which is the same as this angle. So if we take the complement of the angles and swap sine for cosine, or cosine for sine as necessary, we get the quantity expectance of QT. So then we have all the variables we need to compute Bell's function. And when you compute this, you get 2.82, which is larger than 2. Right? Bell's inequality said this quantity has to be less than or equal to 2, and it's larger. So quantum mechanics violates the Bell-CH-SH inequality. And possibly quantum mechanics is correct, but we know for sure that local hidden variable theory is incorrect. So the way you realize quantum computation is by defining a circuit composed of gates, where every gate affects only a couple of qubits and leaves the other ones intact. So let's see a couple of gates. We have the controlled NOT gate. So it flips the second qubit only if the first qubit is set. We have the Hadamard gate. This is the square root of identity, or one of the square roots of identity, I should say, because where the identity does nothing, this does do something. So if you apply the Hadamard gate to a qubit set to 0 or set to 1, then you get the uniform superposition of 0 and 1. But if you apply it twice, then you get your original qubit back, because it's the square root of identity. Then there's the T gate, which really applies phase shift if the qubit is set. And you may be wondering, this is also called the pi over 8 gate, why is there a pi over 4 in the matrix description? Well, the reason is that the state of a quantum system is only well defined up to global phase. So you can take out a global phase of e to the power I pi over 4, and then you get, in the top left, e to the power I pi over 8, and e to the power I pi over 8 in the bottom right also. Then there's the S gate, which applies larger phase shift, and basically for any efficiently realizable unitary, we can generate the controlled unitary circuit, which applies the unitary circuit if the first qubit is set. If it is 0, it doesn't do anything. If it is 1, we apply the unitary transform. And then there's measurement, obviously, but we already know that. This is the symbol for measurement. And really, you don't need to know all these different gates. It really doesn't matter, because with C0, Hadamard, and the pi over 8 gate, you already have a universal set of gates. So those were the basics of quantum computation. Now let's have a look at some algorithms. And where better to start than with Shor's algorithm. So this was the first algorithm that really addressed a real-world problem. At the time, people did not think that simulation of quantum mechanics was a real-world problem. Shor's algorithm was really, really surprising because it breaks RSA. This should not be new to most of this crowd. It also breaks the discrete logarithm, even if it's defined over an elliptic curve. But let's focus on breaking RSA, which it does by factorizing the integer modulus. And this factorization is the second step. The first step is finding the order in the multiplicative group modulo. So if you know the order, then you can factor. If you can factor, then you can compute the order. The two problems are equivalent. And the order, perhaps I should also mention, is the exponent such that when you raise a random number to that exponent, modulo n, then you get 1. I say random because I'm not sure this holds for numbers that are not co-prime with n. But if you start with a number that is not co-prime with n, then you already can compute a factor to begin with. All right. So notice that if we raise a to 1 more than the order, then we get a back. So as we add 1s to the exponent, we go through the entire same cycle again. That's important because we're using the quantum Fourier transform, which is really, really, really similar to the classical Fourier transform, right? So we have a vector. This is the classical discrete Fourier transform. We have a vector of complex numbers, n complex numbers, and we want to map them to another vector of n complex numbers satisfying this relation. So the jth complex number of the new vector is, well, you take some exponential function and multiply it with the k, and then you sum. I never know if there should be a minus symbol here or not. At any rate, I think it doesn't matter for this purpose. So this description of the quantum Fourier transform carries over to the quantum case. The complexity of this algorithm is n log n, where n is the number of values that it touches. All right? In the quantum case, we are not going to explicitly represent this vector. We are going to represent this vector as far fewer qubits. Because remember, k qubits come with 2 to the k complex numbers. And these 2 to the k complex numbers, those will be our n vector elements. So, using Cat's notation, we have a vector x, which really consists of n complex numbers, each associated to a basis state. All right? Meaning that we can represent this on log of n qubits, much denser than this representation. And the quantum Fourier transform computes the exact same mapping as the classical Fourier transform, but from superdense vectors to superdense vectors. So the output is another quantum state, still just k qubits, where the amplitudes are quantum Fourier transform. And the complexity is the same in the number of things that it touches. But there are far fewer qubits here. So the complexity is k times log k, where k is the number of qubits, or with respect to the length, to the size of this vector, It's log n times log log n. So that's really, really interesting, but can we do anything useful with it? Big question. Sure said, yes we can. And in order to demonstrate that, yes we can, remember this property of the Fourier transform, that when you start with an impulse train in time domain, which is a regular sequence of impulses, what you get after applying the Fourier transform is another impulse train, such that the period is 1 over the period in the time domain, and such that any distance with respect to x, or with respect to t equals 0, this difference disappears into the phase. And there is an alignment with the first spike and the 0 frequency. Alright. Now we can show how Shor's algorithm works. So we're going to factorize the product of two large primes. And we're going to do this by finding the order. And we're going to find the order by starting with two quantum registers, A and B, of enough qubits to represent n. And we're going to set, initially they are both set to 0, and then in the first step we apply the Hadamard gate to every qubit of A. So the register A is set into the uniform superposition of all bit streams. Alright. So to describe this, we sum over all possible integers from 0 to 2 to the k. And we take this basis state and scaling coefficient to guarantee that the length of this state vector remains 1. Alright, then in the next step, we're going to apply exponentiation. So we're going to choose a random x that's smaller than n. And then we're going to raise this x to the power a and XOR it into the second register. A is the value contained in the first register, which still contains the uniform superposition of all bit strings. So after applying f, B, the register B contains the uniform superposition of all x to the I, where I is the value in the first register. So in order to describe this, we sum over all I going from 0 to 2 to the k. The first register contains I, the second register contains x to the I modulo n. Now remember what I said earlier about the order. Because once x to the I is larger than n, it will get reduced. Or rather, once I is larger than the order, it will get reduced. So there will be some partial collapse when we measure only B. Well, some meaningful partial collapse. So suppose we measure B and we see x to the power y for some y. Then the first register will remain in the superposition of all states that are compatible with this observation result. And we can describe this as a sum of all I starting from y and adding multiples of the order. Because when you choose any I from this set, then you get a valid exponent that maps x to x to the I, x to the y. Well, this is exactly an impulse train. It has a distance from t to 0, and then it has regular spikes with period order of n. What do we do when we see an impulse train obviously we apply the quantum Fourier transform. And what does this do? Well, the last slide showed what it does. It takes your impulse train, removes the offset from 0, and gives you 1 over the period. The period was order of n, now it is 1 over n, and since it was a discrete transform, that's where the 2 to the k comes from. Of course, this is not an integer, so it doesn't really describe a basis state, but we can... There's a lot of mathematics in Shor's original paper that shows that the basis states that are close to this value have a really large amplitude, and those that are not have a really small amplitude. So when we measure the first register, we will measure a value that's really close to a multiple of 2 to the k over var phi of n. 2 to the k over the order of n. And if you compute an approximation of this number in terms of a fraction of integers, with high probability, your denominator will be the order of n that you're looking for. And then you can apply your standard number theoretic algorithm to turn the order of your number into a factorization. So if it shouldn't work the first time, try it again, but in principle the probability of it working once is large enough to consider RSA broken if we can perform this algorithm. So this is a small example of how the discrete Fourier transform works. So we're trying to factorize the integer 35, and the second register is going to contain 2 raised to the power all possible integers, modulo 35, and when we measure the second register, we measure b is equal to 32. Right? And I think this implies that y is 5. So then we start with a spike at 5, and since the order of n is 12, the spikes are apart by 12. And then when we apply the quantum Fourier transform to this vector, to this impulse train, the distance from 0 disappears, and we get spikes neatly aligned at multiples of the order of n.
Is it 12 or 24?
What the slide says is correct, because it takes into account the fact that 2 is in a subgroup. So this is a small, or I should say just one example of a broader class of problems called the hidden subgroup problem. And it has a very mathematical definition. Namely, we start from a group containing a subgroup which is hidden by a function f. Formally, f hides the subgroup G if f is constant on cosets of H, but different between cosets of H. So you're given access to such an f. The task is find a description of H in terms of generating elements, basis of generating elements. So integer factorization can be described in this form, where G is the integers and addition, and your subgroup is the multiples of the order. Also, the discrete logarithm problem can be phrased in this language, and actually Simon's problem was there before Shor's algorithm was. So really the first instance of a quantum algorithm that solves an instance of the hidden subgroup problem, that was Simon's problem, but at the time we didn't know any practical applications of Simon's problem. That is different now, by the way. As demonstrated by the Even-Mansour construction, in which case we have a publicly known permutation and we want to add some randomness before and after, or some key before and after to make it hidden, make the exact function hidden from the adversary. So it turns out that given quantum access to this circuit, an adversary can extract the key K. But classically, this is already very, very secure. So how does this work? Well, remember order finding. Remember order finding in a group, right? Because what the quantum adversary is going to do is going to add these wires and this permutation, which is, once again, publicly known permutation, and it's going to sort back into the wire. And if you find a full description of this entire system, you can see that f of x for any x equals permutation of x plus k plus the permutation of x. And if you look at the permutation of, at the function of x plus k, well then you get k is cancelled, permutation of x plus k plus permutation of x plus k. Well, you can rearrange these terms, and you can see that these two values are exactly equal. Which means that this function hides the subgroup of order 2 whose other element is k. First element is obviously 0. And the same principle can be applied to attack symmetric crypto systems, or rather modes of operation. So in this second result, this cross or check mark depends on what kind of permutation or pseudorandom function you instantiate the mode of operation with. So that's really rather disconcerting, right? Well, sort of. Because all these attacks require quantum interaction with the secret key material. And there's a good argument to be made that this disqualifies the attack from practical relevance. So when should we consider queries, or rather queries that are quantum superposition, certainly whenever the adversary has a circuit like a hash function or a public key encryption public key, then he can evaluate this on a superposition of values, no problem. In the case of symmetric key cryptography, evaluating the encryption function is performed through an oracle query, and this oracle is provided by the user who is being attacked, and this secret key is stored in classical memory. And in order for this quantum interaction to receive information from the secret key, it has to interact quantumly with classical memory. And that's probably not a realistic model. On the other hand, whenever you model a hash function as a random oracle in order to make your security proof work, well, your adversary doesn't need any secret key or interaction with secret keys to evaluate the random oracle on a superposition of inputs. So this is what gives rise to the quantum random oracle model. Like I said, whenever the adversary has a public key associated with a function, you can evaluate this function on a superposition of inputs. So is it worth studying the situation in which the adversary interacts quantumly with a key primitive? And the 3 papers I cited earlier, they come up with 4 cases in which you might want to study this. Firstly is quantum encryption. So instead of performing a computation that is classically hard to invert, you're going to do something that is even quantumly hard to invert. And, well, a computation that requires a quantum computer to perform, in addition to being hard to invert. And you might want to do this, for instance, to guarantee oblivious transfer with unconditional security rather than merely computational security. I'm not sure how feasible this point is, but who knows, right? When you create circuits designed to be classical, but when you create them small enough that quantum effects start becoming something you have to take into account, well, then maybe at some point you can exploit these quantum effects to engineer the attack of the previous, of 2 slides ago. Thirdly is white box cryptography. Whenever you're giving obfuscated code to the user, and this obfuscated code contains your key, well, if this user possesses a quantum computer, he can obviously run this code on a superposition, and that's no problem at all. And lastly, whenever you have an elaborate protocol proof through a sequence of games, for instance, then you want to take into account that this proof should remain valid when you consider quantum adversaries. So the first 3, I'd say it's okay to ignore those cases. I mean, white box cryptography is the most realistic of these points, and that's difficult enough as it is without considering quantum adversaries. On the other hand, provable security is a big deal. So if you remember nothing else from this slide, please remember that quantum interaction with secret key material, you're allowed to ignore that case. So that was the first lecture. Thank you for your attention. Are there any questions? Yes?
What was the feedback from financial people?
They had questions too. I didn't get rated or anything, but it seemed to me that their feedback was positive and interesting and thoughtful.